Hey guys, this is video project 13. It's over Fourier analysis by Mikey, Gulasey, and Steve Shiner. Okay, so the first thing I want to do is go over the format of this presentation here. The first thing I'm going to do is a quick overview of Fourier analysis, the equations and such, and then at the end I'm going to do a quick demonstration for you guys. Alrighty, let's jump right in here. So, Fourier analysis, by definition, is the study of the way general functions may be represented by sums of simpler trigonomic functions, in our case, sine and cosine. The wavelengths of sine and cosine waves tell us about the structures they represent, as well as their wave numbers. Long wavelengths are associated with large structures and small wave numbers. As you might expect, short wavelengths are associated with the exact opposite, that is, fine structures and large wave numbers. Wave numbers are simply representations of the spatial frequency of a wave, usually in radians per unit distance. We use lambda to represent wave numbers. The Fourier transform, named after the mathematician Joseph Fourier, transforms signals between time or spatial domains and frequency domains. We use it obviously in physics and engineering, and more specifically in our case, computer programming. Discrete Fourier transform, or DFT, converts a finite list of equally spaced samples of a function into a list of coefficients. These coefficients are a finite combination of complex sine waves ordered by their frequencies. In other words, it converts a sample function from its original domain to the frequency domain. We use Fourier analysis every day. For most of us, we had no idea until we learned about it in class. Cell phones, disk drives, DVDs, and JPEG files all involve fast Fourier transforms, or, as they're more commonly referred to, FFTs. The first F in FFT stands for both fast and finite, so the acronym really should be FFFT, but that's just too long apparently for math and programming experts. In MATLAB, the expression FFT of x computes the finite Fourier transform of any vector x. The computation is only a fast Fourier transform, however, if the integer n equals the length of x is the product of powers of small prime numbers. The touch-tone dialing system is a perfect example of everyday use of Fourier analysis. The basis of touch-tone dialing is the dual-tone multi-frequency, or DTMF system. We can think of a telephone dialing pad as a 4x3 matrix. Associated with each row and column is a frequency. The basic frequencies are 697, 770, 852, 941, 1209, 1336, and 1477. This means that the tone associated with any one key you press on your phone is a combination of two signals at two different frequencies. Now, to put this all in use, we can set frequency 1 to 770 and frequency 2 to 1336. These are the frequencies of the number 5. Then, we can create an array of each signal, using the equation y equals sine of 2 times pi times the frequency times the time. The time array, t, which is created by using the rate of digital sound, 32,768 Hertz. We can take the sampling rate and make a time array of t equals 0 to 1 over the sampling frequency to 0.25. Now, we simply create our two frequencies using y equals sine of 2 pi times the frequency times the time array. If we average the two signals, we can play the same tone a phone makes when you press the number 5. Okay, I've already written out most of the code here because I didn't want to bore you guys with clicking on my keyboard, but here goes on the sound. There you go. Thanks so much for your time, guys, and I hope the video helped.